often it's discussed or described as chaos or disorder. And that works for the most part because you can think of entropy is talking about the arrangement of the particles. So we talked about the energy of a system, or we talked about the energy that's being stored in chemicals. We also want to look at the actual arrangement of the particles. So quite often teachers will say, if particles are being spread out or if they're becoming messy, that's a high entropy system because it's chaotic. It's fairly true, and it works most of the time, but the truth is entropy is going to be, or high entropy is going to be the condition that offers the highest number of equal possibilities. So the particles could be arranged in all these different ways, just like your clothes on the floor can be arranged in many different ways. It's all very messy, it's all very chaotic, but they're arranged in many different ways, and it's all equal, whether or not you throw your shirt here or you throw it there. It's all equal arrangement of being somewhat chaotic, or you have the highest number of equal possibilities to throw your clothes on the floor, and there's only one way to fold your clothes very neatly and have shirts in one drawer, pants in another, and have them arranged by order of color. So another way to look at that would be rolling dice. So if I'm going to roll the dice and shoot for 5 of a kind, I'll get that 1 out of every 1,296 rolls. For 4 of a kind, I'll get it 25 times. For 3 of a kind, I'll get it that many times. And for 2 of a kind, that's the most likely. So this would be the system with the highest entropy. It's the most likely to exist. And you would think of it as also somewhat chaotic, because when I roll the dice, I'm most likely to have them all spread out. I'd probably have to cheat and put in some work to arrange the particles, so my dice would have 5 of a kind. Versus I could probably just roll the dice once and get my 2 of a kind, maybe twice. So when we're saying particles are chaotic or in an arrangement that offers the highest number of equal possibilities or the most statistical probable outcome, that's going to be a high entropy. That's when your system is at high entropy. So let's look at something that we can actually apply that to. When can we look at a system and say it is high entropy in chemistry? So if a liquid is turning to a gas, it's gaining entropy. The gas has more possible arrangements than the liquid does. There's more freedom of movement, more ways it can move around. So this is going to be changing from a low entropy to a high entropy, final minus initial. The change is going to be the change of the entropy. S is entropy, by the way. The change of entropy is going to be positive. So it's a positive change of entropy. If a gas goes to a liquid, well now I meant that to be, let's say, sorry, we'll go solid. Make that a solid. If a solid melts and turns into a liquid, then the particles again are able to move around more. So that's again a positive change of entropy. If something is dissolved, let's say you put a sugar cube in your coffee, you've seen that it happens on its own. The particles disperse, they spread around. It's another positive change of entropy. And at this point, I'd like to maybe remind you that when we looked at exothermic reactions, we talked about exothermic reactions being spontaneous. They tend to happen on their own. Not all of them though are, but many exothermic reactions are exothermic. When you have a positive entropy change, that's also considered a driving force for a reaction. It's likely to happen. You drop the sugar cube in your coffee, there's not going to be much of a change of enthalpy in that at all. But what's driving the reaction to occur is going to be that you're spreading the matter out. So it's a positive change in entropy. If you form a gas in a reaction, you're creating all those different arrangements for the particles, so that's going to be a positive change in entropy. Let's see if there's more moles present. So if you took a compound and you decomposed it into other compounds, you'd have more moles of products than reactants. Another positive delta S, a positive change in entropy. Entropy is increasing. These are all things that tend to create a reaction or tend to drive a reaction. When temperature increases, entropy increases as well because you're giving the particles more freedom to move, there's more possible arrangements. So entropy is temperature dependent. And one thing to remember, always look for gas in entropy questions. If you're asked which system has the most entropy, or is the entropy going to be a positive change or a negative change, the very first thing you're going to want to do is look for gas. If you're making more moles of gas, you have a positive change of entropy. If you have the equal number of moles of gas, then start looking at other things. Is something dissolving? Am I making more moles in the product than the reactant? But first, look at the moles of gas. And some examples. So here I have solid calcium chloride, which we had in our lab, becoming aqueous calcium chloride. So it's dissolving, the particles are spreading out. That's going to be a positive change of entropy. Here I have 2 moles of gas, 3 moles of gas on the reactant side, and 0 moles of gas in the product. So I lost 3 moles of gas. So that's unfavored based on entropy. It's a negative change of entropy. And here I have 3 moles of gas in my reactants. I have 3 moles in the products, but only one of those moles is going to be gas. So I lost 2 moles of gas. That's the biggest thing to look at. This is also a negative change of entropy.